All right, ladies and gentlemen, welcome to the last class that we will have together before the final. Um, I am conscious and out of bed, so that's great. All right, ladies and gentlemen, welcome to. That was a bad idea. Let's mute myself in the other tab. Okay. Reagan is teaching herself machine learning, and you end up using Bayes' rule. That's great, actually. A lot of machine learning relies on that. So let's talk about the exam. A lot of you are very frightened. I've been getting emails like, "Help! The final is going to literally kill me." It's not. It's going to be okay. I am extremely remiss in getting grades back for you guys. The scores should be on Blackboard according to the TA. I can check that right now. Hopefully he wasn't just like straight up lying to me. So you should have homework grades. I wouldn't worry too much about your homework. If you turned them all in, you're probably fine. Projects also, if you accomplished something, if you have any semblance of a graph on paper with code, you're going to be okay. Some of you definitely did it wrong. So like if you for some reason got like lines for every algorithm, which is absolutely not correct, that's fine. I mean, just know that if your graph doesn't match the big O, something is horribly wrong. All right, yeah, and you'll turn your projects in next class, at the final. The TA will be there since I actually can't be in a car because if I get in a car crash, I'll fucking die. That was a fun piece of information to acquire. So the TA will be proctoring it. So this is probably the last time you guys will see me. That being said, let's jump into review. Yeah, so don't worry too much about Dr. Chang's stuff last class. Kind of the idea was to give you guys an idea of what number theory is actually for. If I'm talking about stuff like this is odds and evens and prime factorization, it's kind of like abstract, but a lot of cryptography and AI is based on that stuff. So let's go through class stuff. And I'm going to really need you guys to ask questions. Actually, after this, I might have some sort of like video question and answer session if I can set that up. All right, so let's go there. Okay, so yeah. So we'll go in reverse order because that's probably what you guys are most concerned about. The last lecture we did was combinatorics. This one is a pretty rough lecture, honestly. It's a topic that is a little bit hard to grasp. So the things I would like you to know about that are what a combination is versus a permutation. Does anyone in the little chat remember what those two things are? And while I wait for people to type answers to that, I guess I will go ahead and tell you. A permutation is a combination of things where order matters, right? So if I take 6 things and arrange them, I'm going to arrange them in different ways regardless of the order. So I can take a B, C, and I can rearrange them however I want. I could also take from the A, B, C, D, I could only take A, B, or to only take permutations of size 2. So every pair of things in A, B, C, D in every possible order. From this, you should basically, I could give you a question that talks about, like, I have this many things, and I am going to pull this many things out of it. How many permutations are there? I'm also going to give you that formula. I'm going to give you a nice handy formula sheet so you don't have to memorize stuff because I never memorized any of this stuff. So you won't have to memorize that formula. As long as you can apply it and reason decently well about like what a permutation is, you're going to be okay for the permutation stuff. Everyone, okay, chat, say something. I'll refresh just in case everyone's really quiet. Is everyone okay with what a permutation is? Now my chat is gone. Something. Okay, thank you. Great. Yes. So, okay, perfect. Yeah, a permutation is AB and BA are different. Combinations are AB is the same as BA. So combinations are every possible subset of something, but order doesn't matter, right? They're subsets. So there's no concept of order. So just to repeat, a permutation is I draw some number of elements from the set and make every possible ordering of those things. If a combination is I just make every possible subset. So there will always be fewer combinations than there are permutations. For both of these, there are formulas that dictate how many there are. A permutation or a combination, the formula is actually called n choose k, and it's got kind of a weird format. It's actually you can't do it in Google Docs, but it just looks like it's one number on top of another. It's like a fraction, but no bar. So it's just one number sitting on top of another number with white space. That's what n choose k is. So if I give you a problem that just has a number on top of another number in parentheses, and I ask you to evaluate it, I'm asking you to do n choose k. And like, that's important to know. I'm going to give you the formula. So if you can recognize a number sitting on top of another number, that's free points. The generalized pigeonhole principle. Combination ABC is the same as CBA or CBA. Yep, those are all the same in a combination, different in permutations. N choose k is for combinations. I don't know why they named the combination formula, but they didn't name the permutation formula. That's just what they did. The generalized pigeonhole principle is basically a probability of if I have, I don't know, 6 things and I'm putting them randomly into 10 slots, it's the probability that 2 things end up in 1 slot. That's it. I'm dumping stuff into slots randomly. How likely is it that 2 things are going to end up in the same slot? Totally it. There's a complicated formula. I will give you the formula and label it. As long as you understand the concept, you should be able to just apply it when I ask the question. There's a thing called proof by double counting. Is like you show that both sides of the equation are ways of counting the same thing. I wouldn't worry too much about that. If you just memorize that sentence, you should be okay. And so test questions include being like, hey, how many permutations are there of this thing? How many combinations? Basically applying the formula. You might have to do a little bit of thinking. If I ask you like, hey, there are like 3 numbers drawn from 5 things, and then you get to draw another number between 1 and 10. There's an example like this in the slides. So you might have to do a little bit of thinking, but it shouldn't. These are not going to be that difficult. Probability. There's really only 3 things I can sort of ask you. Oh, 4 things I can ask you about. Oh yeah. So if here, I'm gonna make a visual. This might go horribly. We'll find out. All right. I have boxes. Each of these is like a little slot, right? And I'm gonna throw 1, 2, 3. Oh, that's not good. I'm gonna throw 3 things into these boxes at random. So the formula for the generalized pigeonhole principle tells me if I just toss these into these slots, how likely it is that 2 of them will end up in the same slot. So obviously it's going to be 0 for 1 star. It's going to be pretty small for 2 stars. If I have, how many slots do I have? I don't know, something like this. 1, 2, 3, 4. Yeah. If I have more stars than slots, it should be 100%, right? Because there has to, because the regular pigeonhole principle says that if I have more things than I have slots, 2 of them are going to end up in the same place. So that's that. For probability, if you have independent events and you want to know the probability of both of them happening, you multiply them. Something else that I might ask you is I might give you like something like I flip a coin 3 times. How likely am I to get 2 heads and a tail? You can do that kind of question by doing, like literally just counting. Also, it should be like 2/3, maybe 1/3. While I'm painstakingly writing these out, feel free to ask any questions. So like I might ask you something where I'm like, hey, how many THHs are there? Or like how many tails, heads can I get? There are going to be 3 of them, right? Because I can rearrange this in any of 3 ways. And that's kind of interesting because that is a combination. That's how many combinations of HHT there are. So anyway, might ask you that kind of question. The inclusion-exclusion principle, we talk about it down here. It's a fancy name for the fact that don't double count your probabilities. If I'm asking you the probability of getting a king or the probability of getting a heart, remember to subtract out the king of hearts because he's both. So if you're thinking of it as a Venn diagram, don't count the space in the middle twice. Conditional probability. There's a formula for it that will be on the formula sheet. You should understand what it means. It's the probability of A occurring if we know B has occurred. If I know you have studied, yes, that's the intersection. If I know you have studied, I should be able to give a different probability for how you do on the final exam than if I don't know anything about you. So like, if I was going to guess how well a student would do on an exam, that's called the prior probability. That would just be the average of exam grades. If I'm told that, hey, the student studied for 20 hours, well, now my probability is going to change because I have studied for 20 hours. And that means A is probably going to be higher. So yeah, that's it. Know what it means. There's a bunch of sample problems. I think I did a pretty good job of putting sample problems in the PowerPoint. Those are the kind of problems you're going to see. Bayes rules. Bayes' rule is just a formula using conditional probabilities. If you can recognize what is P of A given B and P of B given A in a question, you'll be okay on these. You can just apply the formula. But again, do some of the examples in the slides. Yes, this is like the dumb Trumpers example from the slides. Another really good example is this anonymous quaggas moving around on my Google Doc. Another really good example is this diagnostic example. If you're trying to figure out the probability that someone has a cold from their symptoms, you need to know the probability of colds, the prior probability that a human has a cold, the prior probability of the symptoms just existing, and then the relationship between the two. Fundamental rule of counting, just know the name of it. It's that, I mean, you know what, don't even know the name. It's that if I have 2 sets of outcomes, you can multiply how many there are together. If I have 6 outcomes on one hand and one event and 5 outcomes on the other event, if I combine them, I have 30 possible outcomes. It's just a very simple rule. Yeah, let's go over the cold problem. This is gonna have to be. I'm gonna have to be quick with my formula editing here. So Bayes' rule is P of A given B equals P of B given A, P of A over P of B. So this is Bayes' rule. So imagine someone comes in and says, hey, doc, I have a cold. Well, I'm sneezing. I'm sneezing. Do I have a cold? You're not supposed to see a whiteboard. I'm typing in the document. Can everyone see what I'm writing? Okay, let's get up close and personal with this formula. That is not helping. This is going to be upsetting. There. Ooh, God, why did I do that? All right. Hey, doc, do I have a cold? Well, the doctor is going to say, what the person is asking is, what are the odds I have a cold given I'm coughing? So what you would need to know to figure this out is, what is the probability that a human has a cold? This is just the probability that of everyone in the universe, how many colds are there? If everyone in the universe has a cold, this will be very high. If no one in the universe has a cold, it's impossible for someone to have a cold regardless of whether or not they're coughing. We need to know, what is the probability of coughing? Does coughing contain any information at all? If everyone's coughing, it's not really going to matter. Like, this is not meaningful. And then the final thing is, how many people who cough have colds? That's it. So you just take these words. The best way to do it, honestly, is I write the words in for A and B, and then just put them here. Put them in the things, and then I fill it in. And so like that's basically it. So the trick's going to be going from a word problem where I'm like, hey, 90% of the people in the world have colds. No, it's like, that's an awful world. 10% of the people in the world are coughing. You know, and of the people who are coughing, 90% of them have colds. So basically just figuring out how to translate those into these probabilities. And again, there are some example problems on the slides that I realized that I should provide answers to. So list of things that I'm just going to force myself to do. Provide answers for questions. Yeah, actually, and put together a sample exam. I will do my best to do those tonight, so you guys have tomorrow to look at them. I realize that's not a lot of time. I'm doing the best I can with the spine I have. Let's put this back to sanity. Boop. Does everyone understand the gist of Bayes' rule? Yeah, so what I'm going to try and do is answer those questions or answer selected questions from the PowerPoints and then email those out along with, I guess, as best a sample exam as I can. And I will try and do that We'll start working on that about half an hour after this lecture. Okay. Number theory vocab. So the vocab should be really easy. This is going off. Screw that. Screw that. Those are pretty difficult, and I didn't do a good enough job teaching them to expect you to know them. If you did learn them, good for you. That's gonna be useful to you later on in your life, or not. But learning it will have certainly been a good exercise. Prime, something is coprime if it doesn't share any factors with the other thing. You should know what a proof by contradiction is. If you don't by now, I don't know what to tell you. Greatest common denominator. Euclid's algorithm we'll go over in a second. You should know what kind of numbers there are, injections, bijections. And everyone's favorite freaking problem, prove that like 6 is a number, right? One of these really dumb proofs that I make you do. Just glancing over the quizzes, you guys did a surprisingly good job on these. So, God, I also have to get the quizzes graded by as ASAP. But let's talk about Euclid's algorithm. I believe Dr. Chang was supposed to cover this. If not, I'm going to cover it right now. Even if he did, I'm going to cover it right now. Euclid's algorithm is a way of finding the greatest common denominator between two numbers. Greatest common denominator is something that both of them are divisible by. Will we get quiz 2 back? Man, oh God, if I can manage it, yes, but I will do my best. But you'll probably get it back on Thursday. And if you really want quiz 2, send me an email and I will try and scan your graded quiz 2 and get it to you as soon as I can. But definitely no promises on that. I'm gonna bust my butt to get the practice exam. But I don't know about, I assume unicorns do fart rainbows, so I'm not sure what Ryan's saying. I guess maybe is the correct answer. Okay, look, look, Euclid's algorithm, right? I want to know what number divides both 60 and let's actually say 18. What is the obvious thing here? Probably, does 6 go into 18? Yeah, probably 6. Maybe something else, but I'm guessing 6. So Euclid's algorithm is an algorithm for discovering this greatest common denominator. We want the highest. Okay, 42 does not go into 18 evenly. 12 does not go into 18 evenly. Okay. Leon is just on this bag of cotton candy thing, which I do appreciate. 2 is not the greatest common denominator, right? So, someone's really just highlighting everything. Please stop that. I don't know what you're doing, but I'm not into the pink. So the common factors between the two would be like 2, 3, 6, probably some other stuff. But the greatest common denominator is probably 6. We're going to find out. So Euclid's algorithm, how do I get rid of this pink? No, I'm not going to add a space. It didn't go away. Still not going away. Okay, this is just our life now. This is what we deserve. Yeah. Oh, hey, it worked. Or someone fixed it for me. Okay, look, this algorithm is for finding the greatest common denominator. What it says to do is start off by subtracting the small one from the big one. So you do 60 minus 18. 60 minus 18 is probably like 42. And because of how like division works, these guys should have the same greatest common denominator. And we just repeat the process. This should put you in mind of what kind of algorithm. Everyone type in chat. It's going to be recursive, right? If we were going to code this, we'll code it in a second. We subtract the smaller one from the bigger one. And we're going to just not know how to do math. 38 minus 12. I don't know why it's Tyler the Creator. 36. If I wrote the wrong number. 30. We'll subtract 18 again because we're subtracting the smaller one from the bigger one. So we get GCD of 12, 18. And now we subtract the smaller one from the bigger one again. 18 minus 12 is 6. And then we subtract the smaller one from the bigger one. And now that they're the same, the answer is 6. What did I do wrong here? I got the right answer somehow, so that's to my credit. All right, 42 minus 18 is 26. 26. I'm nervous I'm going to get the wrong answer. All right, well, I'm going to have to start over. Okay, look. Despite the fact that I just got the wrong answer, or I just messed up my math, does everyone get the idea of this? We're just going to subtract. Okay, thank you. Ryan just put the answer in chat. It's still 6. Guys, none of us apparently know how to do subtraction. That's fine. Ryan's got our back. Subtract the bigger one from the smaller one. For those of you who are a little bit more programmy, it would look like this. Do a little bit of a trick here, and that's it. That's the whole algorithm. Big one minus small one. Wonderful. That's it. That's the whole algorithm. So you might have to study that. I'm going to leave this in the chat, or you leave this in the document. And those are the things that I think we covered. I did a bad job teaching. So I'm going to have to just sort of go easy on you for these questions, and including Euclid's algorithm. I might ask you to perform it and tell me what the greatest common denominator is. All of this is very basic vocab. If I ask you to do a graph proof, it's going to be pretty simple. I understand that proofs are horrible. This is stuff we handled on the first quiz. Proof by induction, I'm going to probably give you something along the series kind of thing, as opposed to like a weird one with like tiles and shit. So I'm might give you a series and say, prove that these two series are equal. Those are pretty formulaic. Get it? Because it's a never mind. Convergent, divergent, again, you kind of eyeball it and you're like, that looks like it's going to get big. This one's you just do an addition. Logic, we've sort of gone over to death. We're going to you might have to do some Boolean algebra. Asymptotic analysis, remembering the definitions. I might, ask you to give an ordering of the functions like we did on the quiz. I might show you be like, hey, Yeah, no, this is stupid. Where's the strikeout? We're also going to strike this out because we did one example of that ever. And then finally, sets. You should know what a set is. I have not finished grading them yet. I looked over them, and honestly, you guys look like you did pretty well. I was pleasantly surprised, and kind of proud of you guys. Sets, you should know what a set is. Unordered collection of unique elements. You should know how to do the set operations. A proper subset is any subset of the set. It's any combination of the items. A proper subset is any combination, but it can't include the regular set. So a subset of A, B, C can be A, B, C. A proper subset of A, B, C does not. You can't have A, B, C. I actually told a bunch of my friends the other day that a proper subset of us would have to go get groceries, and I'm a nerd, is I guess the moral of that story. Because I was like, I didn't want all of us to go. Proper subset is always smaller. Thank you, Ryan. That's a great way to explain it. And the null set, the empty set, is a subset of anything. Complement is just everything not in the set. And so here's how I'm picturing this. A vocab section, where I ask you any of the terms where the word vocab is in front of it. Probably maybe a truth table, maybe some Boolean algebra, a domain and range question, maybe. We're definitely going to have this these are definitely going to be on there because they're the things I haven't tested you guys on. And then we're going to get some sample of the other questions. Yeah, I'll give you graphs. That seems fair. You can eyeball them. And then some sample of the rest. Depending on what I see on the quiz, I might give you another proof. Honestly, if you guys did well on the proofs, I might give you more proofs. If you did really badly, I'll just give you a simpler one. And I think that's more or less it. That's what I got for you. I highly doubt it will take the whole 2 hours. I did not do a great job of teaching this class. A combination of not knowing having never taught it before and just getting extremely messed up halfway through. I actually feel really bad for how I did. So hopefully you got some information out of this. Hopefully you gained some skills. I would hate to think that your money and time was wasted. Because I didn't do a great job, I'm going to be grading extremely gently. So if you feel like you only understand 50% of this, if you feel like you are barely grasping how to do proofs and stuff, but you can maybe do simple ones, you're going to be okay. Because I didn't do a good enough job to hold you to a high standard here. I think as a class, you guys are excellent. I was really happy to have you as a group. I was sort of trepidatious about doing a summer class, but you guys were just way more motivated and way more eager to learn than I expected you would be. So I really enjoyed the I'm teaching you when I could. Um, Final grade, I actually don't know when grades are due. I pretty much just have to grade the quizzes, which I hope to do by Thursday, maybe if I'm really, really awake. Um, and the exam will maybe take me 2 to 3 days to grade, and I should be able to put your grades up after that. If you, yeah, I mean, I'm also gonna curve, right? If like all of you get C's, obviously that's more me than it is you. Um, yeah, so let's cool. If for some reason, so there's like a couple of you who are having about as bad a time as I am. I know some of you are having health issues or mental health issues. If you are in that group and you have emailed me, if you're freaking out, if you got hit by a car, send me a note. We can work something out. There's two options mostly is where you take the final a little bit later, or we give you an incomplete. By we, I mean I give you an incomplete. So if you, thank you. That actually really means a lot to me. Um, uh, Thanks, guys. That is really, yeah. I'm glad to hear it. I didn't do as good a job as I would have liked, but I guess I guess you guys learned something. So good. Um, Honestly, there's more to be gained by teaching yourself and like looking for answers on your own than there is from anyone telling you how things work. So I'm glad some of that was um, useful. And honestly, I this is a much harder 203 class than any of your peers will have taken. Most 203 classes cover about half of this stuff. I ran out of other people's notes about halfway through. So I padded it with stuff that many of you wouldn't see till a lot later or ever. So if you felt like, again, if you felt like you only understood half of it, that's fine. That's more than I understood coming out of 203. So for people who want to review, we learned how to prove 6 as a number. Actually, oh shit, I never taught lambda calculus. All right, well, I'll have to let that one go. Yeah, we actually have no idea how to prove 6 as a number. That's if you want to learn how to prove 6 as a fucking number, take Math 301. I know that I think it was like Kate and Hope are the math majors who are going to have to do it. Maybe not. I don't actually remember. But Math 301 is quite the class. You'll like prove algebra works. How to prove mayonnaise is an instrument. I don't know if that's random or if that's a thing I talked about, but here we are. Okay. So what I would like to do now, fortunately, there's too many people watching for me to do some sort of like video review. Oh, if you want to see me, if you want to set up some sort of meeting, I can't really go anywhere, but we can do a Google Hangouts one-on-one if you have questions, if you have concerns, if you need to tell me that you're like grandma ran over your mom and then they both died and you're having a bad time. Send me an email. I'll set something up for tomorrow. We can do a virtual office hours. I think AJ asked about that. Someone else did maybe too. Actually, I don't remember who asked about it, but cool. So let's look at this chat and what would you guys like to talk about? What are the things you are most uncomfortable about? What would you like me to talk about or do an example problem? I have to wait for chat lag to catch up. If you feel good, you can just say I feel good. You guys like what the fuck is this mayonnaise thing? Probability. Okay. Cool. Probability. So let's actually. Oh, yeah. That's my dinner. Don't worry about it. Okay. Chinese remainder theorem is freaking weird, and I'm not gonna. We're not gonna get into Chinese remainder theorem today. Let's do some probability practice. This sounds good. So I can sort of double dip here and do some of the problems from the lecture again. Where did those go? All right, let's do some probability problems. The Mayo is still going. Anukia, I actually don't know which ones you're going to struggle with. That's what I'm sort of trying to get from you guys. Okay, so starting out, sample problems. We're going to start easy. Oh, I'm actually not sharing my screen, so that's great. What are the chances of getting 1 or 2? Let's do a little bit more complicated after this. Sorry, I'm and so this first one you can just list the outcomes, right? Yeah, I would love to see that video. Yeah, but unfortunately you can't. Okay, yeah, it sounds like probability is a huge problem. Find that Chinese remainder theorem video. That sounds good. This one is a listing the outcomes kind of deal. It's easy. This one can actually be done as a combinations problem, permutations problem. Because what it's really asking is, we know that there are 2 to the 5th. Okay, we'll do it in a second. I'm gonna make a list. So you guys get started on like just giving this a shot, and I will find a couple more problems. This is a good one. Oh, yuck. So these are the level of problems you should expect on the quiz, or on the exam. Okay. Yeah, 6-sided dice. Okay, so starting out, this one's pretty easy. There's 2 sort of ways you can do it. Easiest is just list them. We'll talk about the more robust way to do it. Oh, easy way. Well, we got a heads We have this one, and we have 12 things, so 2 out of 12, 1/6. Another faster way to do this would be to, we just know the probability of getting a 1 and a heads is 1/6 times 1/2, and the probability of getting a 2 and a heads is 1/6 times 1/2. So you can just add them because they're non-mutually exclusive events. I mean, wait, they are mutually exclusive events, so you can just add them. So you'll get the same answer that way. So you can either count or add in this case. For the probability of getting at least 4 heads flipping 5 coins, we know that whenever we have some number of outcomes, we can do something like this. This is how many total outcomes there are. This is the first coin, the second coin, the third coin, the fourth coin, the fifth coin. So there's 2 to the 5th possible combinations of results from flipping coins. And you can actually do this as a permutation problem because we want to know if I have this pool, how many ways can I arrange these, right? Think about it. I say like you're not already thinking about it. These are all the possible ways we can get 4 heads flipping 5 coins, which means this is just every permutation of these elements. So what you can do is throw this into the permutation formula. And then divide 2 to the 5th by it. Feel free to ask questions as I go through these. So these should be kind of easy. You guys should have a somewhat of a grasp on these. I mean, this one you can also just think about how to, like, you can actually just write out the outcomes again without having to write out every single one. This one is a conditional probability problem. So yeah, it should be. So take a second, just trying these. So just, what is the, I'm going a little too fast again. So the conditional probability formula is this. Yeah, I need to go slower. I don't know how to type the, oh, there's probably a symbol for this. Okay, this is my conditional probability. Oh, at least. There we go. That's the one I answered. Yeah, you would also have to include heads, 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 heads. Okay. So again, you guys read this problem and you're like, oh shit, this is hard. What do I do? So you have this formula. You have 100 sports cars buyers, 40 bought alarm systems, 30 purchased bucket seats, and 20 purchased an alarm system and bucket seats. If a car buyer chosen at random bought an alarm system, what is the probability they also bought bucket seats? So basically what this is asking is the probability of, we know that they bought an alarm system. We know that this is true. We're thinking about what happens if this is true. Everyone we're examining bought an alarm system. So that means we know that we are given that they bought an alarm system. We want to know the probability that they bought bucket seats. That's what we're asking about. Now that we've filled this in, this should be pretty, now that we've done this, now that we've taken this out, we've seen that we know they bought an alarm system and we want to know about bucket seats. Now we can sort of fill in this probability. Substitute that in for A, substitute bought an alarm system for B, bought an alarm system. And now that we have this, now that we know where things go, well, 20 people out of 100 bought an alarm system. Right, there we go. $20 out of 100 is, I'm going to guess, 20% or so. The number of people who bought an alarm system is, well, these guys bought an alarm system, and these guys also bought an alarm system. So this is 50. So there's, if I randomly choose someone out of this, out of the pool of the people who bought an alarm system, there's a 2/5 chance they also bought bucket seats. And this should be a little intuitive to you, right? Because there's 50 people who bought bucket seats, and 20 of those people purchased both. So out of this 50 people, 20 purchased an alarm and bucket seats. So pausing for a second, can you guys dump some questions or thoughts? Does this sort of make intuitive sense to you? Once you can plug the stuff into the formula, you can sort of just do basic math, I guess. It's not always going to be out of 100, so keep in mind that this probability, you might actually have to compute it. If this was 120, I would have to say this would be 20 out of 120 on the top, and this would be 50 out of 120 on the top. One more time, perfect, okay. So the question wants to know, if someone has bought an alarm system, what is the probability that they also bought bucket seats? And this formation, this thing in math, repeat this, awesome, perfect. And we'll also make sure that I did math wrong. Thank you, Eric. Yeah, we're gonna go through it entirely again. This here, this thing, I'm gonna insert an entire unnecessary, never mind. I was gonna put an arrow. This thing means, what is the probability that A is true if we know for a fact B is true? So here, we know for a fact going into the problem that we are looking at someone who bought an alarm system. That's everyone, that's all of the people we care about. This is not looking at people who didn't buy an alarm system, right? We're guaranteed that they already bought an alarm system. So if we know for a fact that B is true, we know for a fact that they bought an alarm system. Cool. The thing that they want to know is, this is a little bit easier to fill in, is the probability that they bought bucket seats. And let's look at, my eggs are rolling off the table. It's very distracting. Let's look at, what is the probability that someone bought an alarm system? So what is this basic probability, right? This is a question you guys should be able to answer. There are 100 people. There are 40 people who bought alarm systems and 20 people who bought both. So the total number of people who bought alarm systems is 20 plus 40. So if I pick someone at random out of this group of car buyers, I don't know why it's important that they bought sports cars, but if I pick someone at random, there is a 60% chance that they have an alarm system. Because there's 100 people, and 60 of them bought an alarm system. Over here, the probability that someone got both is explicitly given to us in the problem. 20 people purchased both. So 20% of people did both. So now we have everything we need to plug into our formula, right? We care about this. We have this formula. It just says put the number of people who did both over the number of people who did buying an alarm system, and then just do math. Is that a little bit better? Do people feel good about this? Aren't the people who bought both not counted? So these are 3 separate sets. Right, so we got 40 people did the alarm systems. 30 people. All right, who sees the problem here? Who, looking at this problem, what jumps out at you as probably a critical problem that might, in this conception of this problem, this shouldn't have affected any of our work, but it is stupid. Do we, is this math? Yeah, there's not supposed to be a bunch of people who didn't buy cars. But if there is, it doesn't actually change the problem, right? We just don't give a shit about these carless sons of bitches. So let's just change this to 30. So it adds up nicely to 100. So 30 purchased both. Okay. People feeling a little better about this? A little more sense? Again, I actually asked this question on a 400 level exam, and a bunch of people got it wrong. So again, if you can get it, you're ahead of the game. Okay. Reagan and Eric have it, so we're okay. Okay. You have a weighted coin that shows heads 60% of the time. So this one is weird. Honestly, I didn't know how to solve this kind of problem before I prepped for this class. We have our typical outcomes, right? We have our tails, 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 heads, heads, tails, and heads, heads. And the odds of each of these events independently. So we have this weighted coin. It comes up heads 60% of the time. So that means for it to come up tails once, that's 0.4%. That's 40% of the time. If I have 2 events with 2 separate probabilities, I'm allowed to multiply them. So if I flip tails once, there's a 40% chance of that. And if I flip tails another time, there's a 40% chance of that. So together, there's 16% of a chance I flip both. Here, there's a 60% chance I get heads, 40% chance I get tails. Same thing over here. And the probability of getting 2 heads is that. So this is basically I'm flipping a coin twice, let's say. But if we were going to flip, yeah, we'll do that in a second. We'll do that different problem. So this is the same idea of listing all of the outcomes, but now we need to take into account that the outcomes have different probabilities. So you could do this with dice, right? Each individual number would have 1/6. Yep, it would be exactly that, Ryan. So now let's say one weighted coin, one unweighted. Try this. See if you guys can figure out the answer. Shouldn't be too hard. I'm going to grab some water real fast. I'm so good at knowing that I'm not awake. All right. Hopefully we all got it. We all feel good about probability now. Same deal. But now the fair coin on the right is going to have different probabilities. So the probability of getting a tails and a heads is the sum of these two, which is like whoop. Actually do this. This is thing 2. This should be. So it's actually going to be 50%. We have a poodle, some water, and a devil face. So whatever that means. All right. So last question. We got these 2 treasure chests, 100 gold coins, 50 gold and 50 silver. We randomly pick a chest and pull out a gold coin. What is the probability that you pick the all gold chest? So probably we're going to need some sort of P of A given B. What do we know is true? What are we guaranteed is going to happen? So you guys are going to try and fill this in with me. We are guaranteed something is going to happen, and we need to know the probability that we did what, right? What are we guaranteed is true? We are asking about a situation. We're asking about the reality in which we picked a gold coin. And we are being asked about, we're asking about the probability that we picked the all gold chest, right? This is what we care about. Let's see, how do you identify that this is a Bayes rule question? We don't know the probability of two things happening at once. There's no joint probability given in here. We don't see anything where it says there's a 10% chance A and B happened. So we can start filling in things in Bayes' rule. So we want to know the probability of all gold given gold coin. Okay, so now we can just fill this in, right? We know what A and B are. A is the probability of the all gold chest. B is the probability of the gold coin. A is the probability of all gold, or A is all gold, and B is the probability of a gold coin. So now your task, now that you've filled this in, I mean, Ryan filled it in successfully, I don't know about the rest of you. Now that you have filled this in, what are these probabilities? What is the probability of each thing? So what is the probability of just getting the all gold chest? If I pick randomly, what is the probability that I got the all gold chest? I have two things. I picked randomly out of one. What is the probability I got one of the two things? 1/2, right? The probability that I picked the all gold chest, if I know nothing else, is that this is 50%. Right? Good. You guys are getting it. So what is the probability of picking a gold coin? Right? If I know nothing else, I don't know what chest I picked, what is the probability of picking a gold coin? Well, how many gold coins are there, guys? Chat friends. The 5 people who are actually talking and the other people who I assume are the people who sit in the back. Actually, I assume that the 24 people who aren't here are the back dwellers. Yeah, there are 200 coins, and there are 150 gold ones. The probability of picking a gold coin is whatever 150 divided by 200 is, which is 15 out of 20, which is, I want to say 3/4. Is that math? Oh yeah, AJ, you're a back dweller, but you're cool. Okay. What is also, by the way, guys, always sit in the front. Always sit in the front and always make sure the professor knows your name. Those are like the 2 biggest advantages you can have in the class without doing literally anything. So like sit in the front row, front 2 rows, and then tell the professor who you are. That's all you need to do, and I bet you that is worth 5% of your grade. Because there's actually unconscious biases that can crop up when doing grading. If the professor has a prior image of you in their head, if they think you're a good student, if they're like, yes, Reagan sits in the front and participates, and I know who she is, I totally just singled you out. Actually, that's funny that you just said that in chat. Yeah, if the professor has that in their head when they see you on assignments, or if you need some sort of like leniency, you're more likely to get it. This is like okay, well, Leon's doing his own thing. Anyway, a lot of professors actually try and combat this by doing blind grading and stuff. But yeah, that's totally a thing. A lot of life is exploiting weird things in people's brains, which I have actually given a 3-part lecture on how to do, because I've read like 5 books on it. Okay, guys, cashless society is actually not necessarily stupid, but you do need some sort of social credit, some sort of thing to measure productivity. Um, and that's not that's a tangent. Okay, now given that we picked out of the all gold chest, I know that I picked out of the all gold chest. What is my odds of getting a gold coin? So here we know the odds of picking the all gold chest. Here we know the odds of getting a gold coin if we know nothing else. Given that I picked the all gold chest, what is the probability that we got? Yeah, it's one. It's one, guys. That's how math works. So this is an example of just how to take the things from Bayes' rule and put them into the formula. Um, yeah. How do people feel about that? Do we feel a little bit better about Bayes' rule? Okay. When Eric feels better, that's all that matters. A little better. Let me Google. Oh, here. That one's dumb. Googling Bayes' rules practice problems. This is exactly what I wanted. Actually, I have no idea if it's what I want. We'll find out together. You're going to see the doctor about an ingrown toenail. The doctor selects you at random to have a blood test for swine flu. Um, so take a second, read it. So what do we start with? We start by writing down probability of A given B. Yeah, everything about this problem is gross, but that's what makes it so charming. Some refreshing water here. We write down probability of A given B. What are we told is true for sure? What do we know about the world for this problem? For the purposes of this problem, we tested positive for swine flu. I can only assume swine flu is like being a werewolf, but for pigs, where you turn into a pig at the full moon. So it's actually not super bad, right? You're unlikely to maul anyone. You're mostly going to be an adorable yet filthy animal. So this isn't the end of the world, right? We still have a full life ahead of us. We don't even necessarily need to be chained up on the full moon. Um, what do we want to know about? We want to know about what? Um, we want to know if we have swine flu. So this is swine flu. This is test positive. This is swine flu. Well, it's not boar flu, right? Boar flu is another thing entirely. And that's super bad. Okay, this one's actually going to be a little bit complicated. So now we just have to figure out what the heck all of these things are. So let's start with the easy ones, so we can build our confidence. The probability of having swine flu, given that we're in the United States, which is another conditional thing. We know we're in the US. Let's make this math easier. Boom. 1%. 1 out of every 100 person in the US turns into a pig on full moons. I just want you to conceptualize. I just want you to think about how adorable that would be. 1 out of 100 just cute pigs every full moon. It's great. Everyone goes out on the full moon, watches their neighbors frolic. This is a good reality we live in. So we know that for sure. What is the probability of testing positive if we have swine flu? Well, the test is 90% accurate. If the 99% accurate, so this is saying that 1% of the time we get positive if we don't have swine flu. So the probability of getting a positive and having it be right is 0.99. And the overall probability of testing positive is let's see, this is a little bit more complicated than a question I'm going to give you. But let's try and reason it out. So thank you. So let's see. We want to know the probability that a random person taking the test is going to get a positive. So we know that 1% is going to get a positive 100% of the time. And we know that, all right, 1% of the United States. Okay, so let's write this out. So again, the bottom here is just the probability that a person in the United States tests positive for swine flu, right? I grab a random person off the street and I'm like, do you have swine flu? Well, it's possible. We're gonna pull Ryan off the street. Ryan, do you have swine flu? Ryan might turn into an adorable piglet every full moon. We just don't know. We just randomly picked him. So what is the probability that he does turn into a pig every full moon? 0.1, right? What is the probability that he doesn't? 0.99. If he's in this group, so this is us thinking about probability. If he's in this group, the chances that he tests positive are, yes. The chances that he tests positive, if he is a swine werewolf, if he is a pig canthrope, the probability of him testing positive is 100%, right? The test is never wrong if it gets a swine pig, were pig. Okay, you guys got to think about this. I grab a random guy. I grab this hobo. 1% chance he is a werepig. There is a 100% chance that if he is a werepig, the test comes back positive. So what this really is the probability of positive given werepig. Okay. We also need to know the probability of positive given not werepig. So we know that the probability of we know that the probability of being a not a werepig is 0.99 times the probability of getting the test being right. The test is wrong 1% of the time. So it's going to be times 0.99. So these are all of the ways you can test positive for this test. Okay. Again, this is a more complicated problem, right? It's got layers. It's like a onion. It's like, it's got layers. So if we add these numbers together, that's the probability of testing positive. Are we more confused, less confused, or the same amount of confused? Minus all of the things I said about werepigs, which I assume was only confusing. I accidentally closed my window. Okay. Oh no, chat disconnected. Did I lose? Is anyone here? Did I lose everyone? Because I can't see my own feed here. Now I'm just talking to myself in a room. I'm still on the internet. I can't see the chat anymore. Okay, it worked on this computer. Awesome. No, your exam will probably not be this complicated. Oh, we're gonna get this. Okay, we did it. My other computer just crashed. That's fine. I don't need two computers. The exam. So yeah, the exam will not be this complicated. This is a question on the hard side, but hopefully you guys sort of followed my reasoning here. Yeah, I just lost access to this page on the computer. You guys can't see. Hold on. This computer here lost access to the page with my chat on it. Okay. Let's do one more Bayes rule question. We're just all Bayes rule all the time. Sorry, I shouldn't let there be dead air here. Oh, you guys can probably see what I'm doing. Well, we're taking that window away. Oh God, what's going on? Merge that window. I'm like, okay, there we go. You guys can see the appropriate things. I'm just Googling Bayes theorem practice problems. It's important when you're a teacher to just know how to keep talking, even though your brain is doing something completely different. A lot of times when I'm like saying random shit about pigs, it's because I don't know the answer yet, and my brain is solving it while I talk. God, I wish I could teach a public speaking class, because I'm a lot better at that than I am in math. Someone look up a base rule practice problem for me. Yeah, everyone go home to your parents and be like, I just spent thousands of dollars to hear my professor talk about werepigs. Okay, here we go. We're gonna do this one's like we're gonna change this one because it's too dark. By the way, there was a professor who used to on his exams give a question about people jumping out of the World Trade Center and how long it took to hit the ground until he got someone whose parents were in that horrible tragedy, and then he wasn't allowed to teach undergraduates anymore. Um, we're gonna change that. Okay. So in a particular pain clinic, 10% are prescribed narcotic painkillers. Overall, 5% of the clinic's patients are super happy. I don't actually mean to equate being addicted to painkillers to being really happy. I'm just um I don't know what's going on in any of your lives, so I'm just trying to take it away from something that could conceivably be upsetting. Um okay. So, what do we got here? What do we know about the world? We know that our patient that we're thinking about, the patient that we want to know something about, is super happy. So we are given that they are super happy. And we want to know the probability that they are prescribed pain pills. Um, we have our Bayes rule here. That says, am I in a formula here? No. Super happy given prescribed pain pills. I really should have changed the rest of this example, but here we are. Probability of A the probability of okay, do we have all this information? I have no idea. So let's look. So what is the probability that someone is prescribed pain pills? Do not take this as an endorsement to try narcotics. Okay? It's not gonna make you super happy. So probability of being prescribed painkillers is 10%. Oop, wrong one. Probability of being super happy is 8%. Probability of I'm sorry, probability of clients, patients being super happy is 10. And the probability of being prescribed painkillers, of being super happy if you're prescribed painkillers, given that we know you're super happy, we get 0.8%. Yeah. Opioids are bad. I am currently on some opioids, but that's because my life sucks. But yeah, okay. Bayes rule. If you can understand Bayes rule, probably these questions that are the conditional probability ones aren't going to be super hard. What if I ask you something like, you're going to need to go back to the combinatorics lecture and look up the relevant formula while I eat this egg. This egg is pretty raw, so that's gross. Huh. That's life note. Do not undercook your hard-boiled eggs. All right. So first of all, is this a permutation or a combination? Which formula do we use? In lotteries, does order matter? I'm going to go ahead and say it matters. So the formula for, hopefully you guys look back through the notes. The formula for picking 3 things from a set of 10 is n factorial over n factorial over n minus r factorial, where n is how many things you're picking. So we're going to have 3 factorial over, oh, nope, this is how many things you have. I'm sorry. You're picking out of 10 things. You're picking 3 of them. And this is how many combinations of how many permutations of the number between 1 and 10 there are. If you pick 3 of them. Oh, that was not articulated well. So it's not 3 choose 10, right? 3 choose 10 is for combinations. We actually care about order here. So we're going to use the permutation formula, which is, again, it's this n factorial over n minus r factorial. So this is every combination of 3 numbers between 1 and 10. Okay. Next up, how many combinations of 1 letter are there? And we could do something like 26 factorial over 26 minus 1 factorial, which is just going to be, actually, yeah, I mean, this math makes total sense, right? What's left over is just a 1/26. So there's 26 different ways to choose a single letter, which obviously you guys knew off the top of your head because you went to elementary school. So if this is my way of choosing any combination of 3 numbers between 1 and 10, or any permutation, sorry, and this is my way of choosing a letter, what can I do with these 2 numbers? I'm allowed to multiply them, right? Because that's just how math works. It's this fundamental principle of counting. Does that make sense to any people? That's the kind of problem I'm probably like. That's the kind of thing that could show up on the exam. It's a pretty simple application of the formula. Yep, they're independent, so we can just multiply them. If I have some number of outcomes and I combine it with some other number of outcomes, I just multiply. What else can we go over? What if it was combinations? It'd be basically the exact same thing, but with the combinations formula. Which is n choose k, right? And it's n factorial over r factorial times n minus r factorial, and I will give you these formulas on the exam. So it's mostly just recognizing what is a permutation and what is a combination. All right, what else do we want to go over? And the answer can be more of the same thing. Yes to Leon, Brian, and Eric. Why did my thing go away? That's weird. Oh, shit. I closed the window that I was sharing with you guys. Okay, so yeah, what other things do we want to talk about? I like lost every window I have. There we go. Yeah, I will say if order matters specifically in the problem. Any other more commutations and permutations? All right, let's do it. Okay. See that one. Take a minute. See if you can figure out what formulas to stick this into. Any kind of proof you think we should go over? Oh man, honestly, like really done a lot of proofs. Like I don't know, I've already sort of like immersed you in proofs. So I think you'll be good, but why don't I go grab my proof book and see what I can do? All right, the book was not under my bed where I left it, so I don't know. I'm gonna just come up with a proof off the top of my head. Um, so yeah, these shouldn't be too hard for you guys. But first of all, what is the first one? Is a permutation or a combination? Do we care about order? Not really, right? We just care about how many, like just the combinations. So what is the formula for that? It is, I already forgot it. This is n choose k, right? So it's n factorial over r factorial times n minus r factorial. So we just basically plug in, it's 52 choose 5. I don't know why that's a 1. All right, and the second one is a permutation, right? Order now matters. So it's going to be, we have 10. This one's a little more complicated, right? Because we are choosing from this set. Two, three, four, five. So from this set of 10, how many ways can we arrange? Hold on. I'm like blanking on how to do this. So we're gonna just take it out. And I can do that because my spine's messed up. I can just claim that it's not that I'm bad at math, it's just that I don't have a spinal cord anymore. Okay, so basically the combinations and permutation problems are pretty much going to be, can you figure out which one is a combination, which one is a permutation, and can you plug the numbers into the formula and maybe do a multiplication at the end? Thanks, Ryan. No, I appreciate that. So that's more or less those problems. Trying to think of a proof I can go over. Actually, you know what I'll do? I'll put this on my list, is I'll just share out the quiz. God, I'm gonna try and do this anyway. Share out the quiz with solutions, so you can try those problems again and see what the right answer is. Try them again when you're not like freaked out and nervous. Anything else we'd like to go over? There's probably going to be a Euclid's algorithm problem. There's probably going to be basic permutations. There'll probably be a proof. There will probably be a Bayes rule question and a conditional probability question. And then assorted other stuff that you've seen before. All right. Anything else you guys want to look at? For the combinations and the probability, there's a lot of questions online. Also, there's a bunch of questions to practice from in the lecture, which I will, again, try and release results for after this. So, thoughts, questions, concerns? Project is due on Thursday. Bring it in as just paper, right? Print out your graphs and your code. By the way, some of you guys were struggling to use Excel. If you guys, okay, so I assumed a lot of things that I maybe shouldn't have. For one, this is a really useful tool. I'm going to do a quick couple programming and important for your life things. So here's an important programming thing that you'll probably want to know for your regular life. All right, we're gonna get out of that, clear. Just so you know, just so I can explicitly state this, this is called output redirection. And this will put any of what your print statements say into this file. Another important piece of information is there is a format called a CSV file. CSV files just look like this. They are called comma-separated values. And they can be read in by spreadsheet programs like Excel. For those of you who didn't know how to, weren't comfortable with Excel, I would highly recommend becoming comfortable with Excel. I'm not going to really help you with that, but being able to use that program is like a strong prerequisite for anything you will ever do. So if you are not familiar with it, if you don't really know how to graph things, if that was part of the project you struggled with, make a point of learning how to do that, because that is a sort of basic level skill that you need to have. Ryan, if your graph was a straight line for, I don't remember what the exact algorithms were. If your graph was a straight line for minimum, or what else was there? Any of the O of n things, then you're fine. It's supposed to be a straight line. If your graph was a straight line for permutations or binary search, for anything that does not have a big O of linear, then you might have some problems. Merge should be log n, right? So merge sort should look like a curve like this. Bubble sort should be an exponent. Anything where you did curve for bubble should be n squared. Anything where you do 2 for loops should be n squared. Anything that you did 1 for loop for should be a line. Anything where you did if binary search should have been a curve that levels off. If you didn't get that, I don't really care as long as you show me code and show me some graphs. But you should know that either just pick a random number. It doesn't matter. Just has to be something in the list, or pick something out of the list. Shouldn't matter. Right. So if you're getting weird graphs, there's two possibilities. One, you coded your algorithm extremely inefficiently, and in that case, it will have a worse big O than it should. So if your min function is a quadratic, you did something horribly wrong. The other option is if your search has a lower thing than you meant. If your minimum function is log n, you either didn't test your code adequately, which you always need to do. God, I could talk for like an hour about coding discipline. Or you broke the laws of physics, or you're using a quantum computer. Oh yeah, sure. Let me just show you one more time. It's pretty simple. On the terminal, it's just this. It's just this bracket, this little whatever it is. I don't know what it's called. And it will just dump all of your output into out.txt. If you're doing this on the GL server, you will have to move it back to your computer. There's a couple ways to do this. If you're using Windows, there's a program called WinSCP. And if you're a transfer student, this shit is important because they're going to assume you know this in 341. So WinSCP lets you transfer files. It's a program you can download from a sketchy internet site. If you're on Mac, it's actually a terminal command. I don't actually remember my password. So all this is like a copy command. You put in your username at the server, colon the file you want, and then you say dot to copy it over to your computer. Once you have that, you should just be able to open it and copy and paste it into Excel. This works for anything. This will always do output redirection. Yeah, I mean, if you just did regular output, that's totally fine. I just didn't want to assume that you also remembered file IO. It's a little bit easier to just do output redirection. So however you did it, it doesn't matter. What I wanted you guys to get from this is a little bit of practice coding and more freedom than you're used to, right? In 201 and 202, they're like, here is exactly how you're going to do this. I wanted you guys to just be able to, I don't know, code bubble sort without a professor telling you like to use these function headers and whatever. And also, I think it's kind of cool to be able to see a graph of your big O and see that it's real as opposed to just a math thing on the board. Other questions? Thoughts, concerns? This is probably your last time seeing me. Okay, I guess I have 3 more things to say. Also, there's a small chance that I will get wheelchaired into your exam and get to proctor it myself, which I would actually really like to do. So we'll see if that happens. But in case I don't ever see any of you again, my last 3 things are, first of all, if you, I don't know, like this lecture or liked the class or whatever, I would love it if you friended me on Facebook. I really like to be able to keep up with my students. If you have something cool you want to say, just say hi from time to time. Not many students actually do this, but it's really like, I don't know, it's nice to see how you're doing. It's great I love like having former students ask me for ask me programming questions. I've like helped people with 341 and other classes. And some of you, if you need recommendations for stuff, there's a a number of you that I would happily write recommendations for. So keep that in mind. The other things are if you liked my lecturing, one of the things that I discovered during this class is there's actually not a lot of great YouTube videos on a lot of this content. So a couple of my friends and I are actually creating a series of YouTube videos covering stuff like this, covering machine learning, covering encryption at like kind of a basic level and a technical level. So if you are interested in that, let me know. And then only one student has ever taken me up on this, but there are also a bunch of my friends from various different disciplines give weekly video talks live over Google Hangouts that people are also welcome to. Some of it's stuff like physics of sailing. Some of it is stuff like creative writing. I give mostly math and psychology talks. I don't think anyone's actually going to sign up for that because you actually have to face-to-face with a bunch of people you don't know. But I think I'm doing like introduction to game theory next week. So yeah, if you're interested in both videos or coming to an intimidating series of video lectures, let me know. And I really hope to hear from you guys. That being said, good luck on your final. Like I said, don't freak out. All of you are pretty smart. I think you're going to do fine. And good luck in your life. Oh, and if you have questions or things you want to talk about, send me an email. I'll do my best. All right. Bye, guys.